All right, Earth Science 11, welcome back to this week's edition of me talking. All right, this week we're talking about air pressure and wind. So let's get started. Just to let you know, there's going to be a couple of slides that'll be revision, and then about maybe 3 or 4 slides of new information for you. So this week's a good week to put everything together that you've learned. So this is old news for us, just giving us a new perspective. What is air pressure? A little bit of a reminder. It's caused by the weight of all the air in the atmosphere that's pressing down on you. So if you look at the bottom here, underneath this big column of air, you're going to see that there's a huge amount of air molecules that are sitting on top of you. They each have a little bit of force of gravity pulling them downwards, and as it pulls down on you, it's going to add some weight to you. So our standard pressure is around 1,000 bars. To maybe put that in numbers again that might be more familiar, you can think of that as roughly 15 pounds of pressure for every square inch, or around 1 kilogram for every square centimeter. That's about how much weight the air is resting on top of you there. It changes with height. You can see that if I'm down here, I've got this whole column of air above me. But if I'm up here, then the air that's sitting on top of me is going to be a lot less, obviously, so less air pressure when you move up. And changes in pressure, they do cause changes in weather. So we kind of reviewed this as a new picture to go with it. But this is the idea that in areas of low pressure, the wind is rushing inwards. You can see these arrows kind of all moving towards this low pressure area. When they get there, there's nowhere for them to go but up. They're all being kind of squished together. So as they go up, they rise. We also know that air that is forced to rise tends to get colder as it goes further away from the Earth. As it gets colder, it can't hold as much moisture anymore. So the relative humidity, how moist the air is, as a ratio of how much it can hold, that's going to get higher and higher. We know that cold air can't hold as much water. So as it gets cooler, that air molecule is going to be forced to condense. You're going to get some clouds and you're going to get some rain. The opposite is true for the high pressure. So in high pressure, there's a lot of pressure here. We all know that when there's something like a gas or air that's in a high pressure area, it's going to want to move towards less pressure. So it's going to move away from a high pressure area. Because it's moving away, it's not just going to get less and less air there. So it's moving away at the surface, but that means it's going to need to be replaced by air that's coming in from the upper atmosphere. As it does that, the air sinks. So we know that as it sinks, it's going to get warmer. Warmer air can hold moisture. So there's still the same amount of moisture. The absolute humidity will be the same, but the relative humidity will get lower. So it has, 1 gram of water, for example, for every cubic meter of air, but it's going to be able to hold a lot more. So it's going to feel more and more dry as it goes down. That's going to lead to clear skies. The clouds are going to disappear if they were there. They're going to disappear as they go down and they warm up and they're able to hold more moisture so that air vapor will kind of be absorbed by the air, you could say, and so the clouds will disappear. So this is all old information for us. All right. Now we're going to look into a bit more detail. This is pressure on weather maps. Now this is kind of overwhelming to see all at once, but this is what a weather map could look like. So when you have an area of low pressure on a weather map, it's indicated by this L here, we can see in the middle, and areas of high pressure, these are going to be indicated by the blue H's like this. This is an area where high pressure means it's higher than everywhere around there. Now, the lines that you're seeing here, these orange lines, these are called isobars. And this is one of the notes from your note sheet. So the isobars are lines that connect areas that have the same air pressure. So anywhere along this line, the air pressure is 1,020. Anywhere along this line would be 1,024 millibars. Anywhere along this line would be 968. Sometimes they'll just show the last 2 digits. So the lowest here is 960, but this particular line here is 968. The highest here is 1,026, but this particular line shows 1,024. And we measure air pressure, just a reminder, we measure it with a barometer. That's the scientific device that we use to measure air pressure. You can also note that where the isobars are very close, like close to this L right here, this indicates that the the pressure is changing very, very rapidly. So that means not too far away. So say over here, for example, there's the pressure is a lot higher than it is over here. So in a very small distance, there's a huge difference in pressure. Now, when this happens, it means that there's going to be a lot more force pushing the air from here over into this direction here. So when you see the bars being close together, it means that you're going to have a lot higher wind speeds. There's a big difference in a very, very small area, so you have high wind speeds. Somewhere over here, where you can see this difference here is the same as the difference here. For example, these are 2 isobars away, which means it's about 8 millibars difference. So this is 8 millibars. You can see it's very close. This is 8 millibars. You can see it's very far apart. So this is not going to be as windy. So when they're farther apart, you're going to get a lot less wind. Okay, and that's how we can tell what the wind speeds, or we can predict what the wind speeds would be based on the different pressure and based on how closely those isobars are together. Now, when I'm drawing this here, I'm showing the wind going in this direction, but that's not exactly the whole story. It's not just going to go directly from high pressure directly into the low pressure area. It is going to take some different route, and that's because the Earth itself is spinning. So winds will move from high pressure to low pressure. But when we're talking about larger areas, it doesn't blow directly from high to low. So we're going to watch a quick video embedded within the video, so meta. We're going to watch this quick video, and we're going to show why this is the case. So in the northern hemisphere, winds are always going to be diverted to the right. In the southern hemisphere, winds will always be diverted to the left. And we'll show this quick 2-minute video to
Coriolis effect, an object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by 2 people on a merry-go-round that spins like the Earth but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away. The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels farther. In the southern hemisphere, rotation is clockwise when viewed from over the pole. Again, the ball follows a straight course, but its apparent flight path is diverted. This time, the effect is to divert the motion to the left. On Earth, all free-moving objects, including masses of air, are subject to the Coriolis effect. In the northern hemisphere, objects are diverted to the right, as viewed from the direction of original movement. In the southern hemisphere, the deflection is to the left.
Okay, so what this is saying is, because if you look at the way the Earth is spinning up here, it's spinning, if you're looking at it from the top, it's going to look counterclockwise. So because it's spinning counterclockwise, if you were to throw something from the North Pole, say towards here, although your path that you're throwing it on, which is a different color, that you're throwing it on initially is going to be straight south, for example. But as you've moved it straight south, let's say you're throwing a ball with a huge throw that's throwing it straight south, this part, the equator down here, in that meantime, will have moved from here to here. And so what that means is that this ball is not going to end up at this location here. The ball is going to end up somewhere maybe down here. And so if you were standing on the Earth, you would see, or you're standing in space even, you would see this sort of curve towards this way. So even though you're aiming it down here, the Earth has sort of moved out of the way in the meantime. And so by the time the ball lands, if you throw it really high and you throw it down to the equator, by the time it lands, it's going to land here because the equator is already moved out of the way. And so you're always going to see, let's say the air is trying to go from high to low down here. Well, you're aiming for that high, but then it's going to turn to the right. You're going to miss that low. And so as all the air is moving away from the area of high pressure, it's going to do the same idea. As it moves away, it's going to veer to
Coriolis.
oops, it's going to veer over to the right. Same thing for an area of low pressure. The area is trying to move towards the low pressure, but every time it starts to move towards the low, it's going to veer to the right. And so we're going to get this sort of idea here. And this is why we'll get, in general, clockwise winds going around a high pressure area. We can see here that they're all sort of generally flowing in this direction here. And in an area of low pressure, we're going to see that it's all going to generally move in this counterclockwise direction here. There is another link if you're interested in seeing another video that might explain it differently for you in the slides. Okay, so a few examples. So this is an example on the left-hand side here, showing that what it's going to look like in terms of isobars. When the isobars are very close, we're going to have very fast winds. Isobars a bit further apart, we're going to have slower winds over here. If we were to draw this weather map here for the high pressure and low pressure, we know that it's going to move away from the high, and it's going to veer to the right as it does. And then towards the low, it's going to move towards the low pressure, but also veer to the right. So as it's going up, it's going to turn to the right. And as it's going this way, it's going to turn to the right. And so one way of looking at this, one helpful tip, and it will help you with some of the questions in the worksheet, is this right here. When the wind is to your back, so if you're standing somewhere and you turn around so the wind is pushing into your back, you can always tell where the low pressure area is. It's always going to be to your left. So let's think about this. If I'm standing and the wind is to my back and I'm facing this direction here, well, where is the left? Where is the low pressure area? It's going to be to my left. So if I'm facing this direction here, the low pressure area or the left is going to be kind of this direction over here. If I'm standing over somewhere over here, and the wind, looking in this direction here, the wind is going to my back. Well, where is the low pressure area going to be? It's going to be to my left. So this is a nice trick to always keep track of where exactly that low pressure area is going to be. It's always going to be to your left. Okay, this is the example question on the worksheet, so hopefully you're going along with it. Now the question asks you to add the letters H and L to the map to identify the high and low pressure areas. Well, if you look here, we're going from 1024 to 1028. So the pressure seems to be going up, and that means that the center of this is going to be the highest pressure area, this area right here. Now, if you look down here, it's hard to tell from this specific one here, but it's going from 1016 to 1022 or 1020 to 1022. It does seem to be getting higher. Another clue here is that the wind, this arrow here, looks like it's going clockwise. And we always know, like we saw in a couple of slides ago, if the wind's going clockwise, it's high pressure area. If the wind's going counterclockwise, it's a low pressure area. So this is, I didn't mention it before in the previous slide, but this is this part here. It always is clockwise around a high, and we call that anticyclonic. It's counterclockwise, which we call cyclonic, around a low pressure area. So counterclockwise, or also what's known in meteorology as cyclonic, because that's what a cyclone does in the northern hemisphere, like a tornado or a hurricane. And this is anticyclonic, or clockwise around a high pressure area. So for this right here, we see that it's going clockwise. That tells me it's a high pressure area. Here, the wind is blowing counterclockwise. So, or cyclonic, that means this is going to be a low pressure area. Let's see what else there is. This right here, you can see that the pressure is going from 16 to 20. So this is a low pressure area. Here again, going from 1020 to 1024. So that means this is the lower of those areas. So yeah, you can definitely take a lot from these maps. So this would be a high pressure area again, and we know that because the wind is going uh, clockwise, and also because it's a really high value. So 1013 is the average, so larger than that means that it's going to be higher than normal. Okay, so what are the weather conditions in North Carolina? So North Carolina, let's take a look here. North Carolina is right around here. North Carolina, we know it's going to be a high pressure area. High pressure means that it's going to be clear skies. We talked about that a couple of slides ago. And also it's generally going to be cooler than the surrounding area in a high. So one way that you can think about that is that in a high pressure area, it means that it's actually, you know what? That's fine. We're going to ignore that part for now. Just keep in mind that high pressure will often be cooler. I don't think we talked about this a couple of classes ago, but it's a bit complex to go over in this one slide. New Hampshire, that's down over, where is it? New Hampshire's up here. So New Hampshire is going to be low pressure. Low pressure generally means cloudy skies, and low pressure often means warmer weather as well. That's not as important as the cloudy skies part, the low pressure part. And Indiana. So Indiana is right here. One thing that's different about Indiana compared to the other two locations I mentioned is that it's going to be quite windy. And we know that it's going to be windy because these bars are close together. So whenever there's a close isobars, it means it's going to be a little bit windier. In general, it looks like it's slightly higher pressure here, and also that means it's going to be clear skies. So a few example questions there. Okay, last bit of information for you. This is just more bonus material than anything, but this is about winds by the water. So we mentioned a few classes ago that, or a few weeks ago, that water can absorb more energy than land before it changes temperature. So if you think about boiling a pot of water, if you were to put an empty pot on a stove, that metal would get hot very, very quickly. So metal doesn't take a lot of energy to change its temperature, but water would always take a lot longer to boil than that piece of metal. And even on a hot day, if you touch your seatbelt in your car on a hot day, you can feel that that seatbelt is a lot hotter than the surrounding air. And so that's because solids like metals or dirt in general, land in general compared to water, will be able to change their temperature quite rapidly with heat, as opposed to water, which is going to take a lot longer to boil. So that means that the land is going to be gaining or losing energy much faster. So the result of this is that during the day, when the sun is shining down on the land and the sea's temperature is not going to change that much. The water temperature might go up by a degree or two, but the land might go up by 5 or 6 or 10 degrees. And so what that means is that compared to the water, the surface is going to be much, much hotter. So the air above the surface is going to be much warmer. And that means that it's going to be pushing upwards because warm air, we know, rises. As it rises up, it's going to spread out. As it goes over the water, it is going to cool down. And so that's why we're going to get these sea breezes during the day. So we get warm air pushing up, forming a cycle, and the cold air blows in. And so that's why the sea breeze is going to keep us cool during the day. So sea breezes during the day, it means that you're going to keep a little bit cooler. Now at night, it's the opposite thing that's going to happen. The ground is going to get cold a lot quicker than the water. So that means the ground might drop by 10, 15, 20 degrees, whereas the water won't go down to be as cool as the sand around it or by the beach, for example. So that means that relatively speaking, the water is going to be a lot warmer than the ground. That means the air above the water is going to be a lot warmer. And so that means that we're going to get what's called a land breeze. So we're going to get this cycle here. Warm air rises above the sea, spreads out. As it goes closer to the air, it cools down a little bit, and that pushes it outward. So you're going to have this land breeze where cool air is going to blow out over the sea, but that also means that it's being replaced by warmer air coming in from above all the time. So that's going to keep you a little bit warmer at night because that warmth from the sea is kind of making its way over to you. And during the day with a sea breeze, it's going to keep you cool during the day as the cool sea breeze kind of pushes in towards you this way here. So that's that for the week. Hopefully you learned something and enjoyed yourself. And if you have any questions about the homework, let me know.